Welcome to the Cyber Science 2020 conference. For those joining today, just a reminder that Cyber Science is a multidisciplinary conference on cyber. This is the 6th edition of the conference that it was supposed to take place in Dublin, Ireland, but due to the unfortunate event of the global pandemic, we have moved it online. So the conference lasts 5 days. This is the second day, and please feel free to join as much you like. So you can pop in for the sessions that you are interested in, the ones that you have time for, all of them. In general, we have 2 parallel sessions. Sorry, just a minute. In general, we have 2 parallel sessions. This is session 1. Please check online the schedule and decide which session you want to attend. We have as well some keynote speeches that they are joined for both sessions. So there is no clash on that. Today we have a keynote speech from Dr. Philippa Spencer from the STL at 3 p.m. UK time. And a second one from Dr. Gerson Nurse from University of Kent at 6:30 in the evening, UK time as well. So without losing more time, this is session 1. This is track 3, exploiting deep learning for cybersecurity. We have 4 presentations this morning, split by a break of 1 hour between 12 and 1 p.m. And I think that we can start. So please say hi in the chat if you are attending, and if you want to ask any questions to the speakers, use the Q&A option at the bottom of the screen. I will be moderating the questions and ask them at the end of the presentations. So the first speaker today is Suleiman Yerima from Montfort University, presenting his paper about mobile botnet detection, a deep learning approach using convolutional neural networks. So Suleiman, the floor is yours.
Thank you very much, Arno. Thank you for that introduction. Good morning, everybody, and welcome to my talk on mobile botnet detection, a deep learning approach using convolutional neural networks. So, okay. Some problems with navigation here. Okay. Go back. So this is the outline of my talk. I'll give a brief introduction. Then I'll go on to talk about the motivation of our study, the approach that we've taken, experiments that we've undertaken to look at the use of CNNs for mobile botnet detection, the results that have come out of these experiments, and the conclusions that can be drawn, and the future work we intend to continue to do in this space. So my name is Suleiman Yerima. I am senior lecturer in cybersecurity at Montfort University, and I'm also a member of the Cyber Technology Institute, which is a research institute within the Faculty of Computing, Engineering, and Media. My research interests at the moment revolve around malware, mobile security, behavior-based authentication, and anti-forensics detection. So my co-author for this work is Dr. Mohammed Alzaylaee, who is an assistant professor at Al-Qurra University in Saudi Arabia. He obtained his PhD from Queen's University last year, and he is also having an interest in research around mobile malware detection, dynamic analysis of mobile malware, as well as machine learning. So that's that about the authors. So basically, to begin my talk, as you all know, Android is the leading mobile operating system currently in terms of percentage of users worldwide. And as a result of that, it's very, very attractive to malicious actors. So it is the platform that is most targeted by malware. There are various families of malware on the Android platform, and some of these can be considered to be bots. For example, we have families like TigerBot, Robber, Not Compatible, UnserverBot, Yerima, numerous families that are capable of turning Android devices into bots that become part of a botnet. And as you know, a botnet is simply an internet-connected device that is under the control of bot masters and uses a command and control channel to receive instructions to carry out different types of malicious actions such as DDoS attacks, spam distribution, phishing, click fraud, theft of personal data, and so on and so forth. So the purpose of this work is to look at using deep learning for Android botnet detection based on convolutional neural network, which is an approach that is a deep learning approach that has been popular in the use of in its use for image classification, video classification, natural language processing, and so on and so forth. The approach that we are proposing is based purely on static features, which means we're extracting the features from the applications without actually running them. And the idea is to use this to be able to classify an unknown application into either a botnet application or a normal application. And the benefits of this is that you will have a proactive way of filtering out bot apps from unknown apps. So you can therefore filter potentially harmful apps before they get onto your phone. And also, we want to leverage the power of convolutional neural networks with the aim of reducing the pre-processing that is done in the process of training a classification model. So as I go on in my talk, I will emphasize how we've applied convolutional neural network as a means to reduce the feature pre-processing steps that are usual when machine learning algorithms are applied for classification of botnets or Android malware in general. So in a nutshell, this is a summary of the way the system works. We have here the feature extraction, which occurs with the use of botnet apps and normal app samples. So we extract features from these because we want to do supervised learning for classification. So we need both classes of botnet apps and normal apps. And the type of features that we extract, like I mentioned before, are static features, but we do represent them as binary features. So we are looking for features that are either present or absent in a particular application. So when we vectorize this, we then apply this directly to a convolutional neural network based classifier, or we apply this to train a convolutional neural network. So once we've gotten our convolutional neural network, it is ready to be used to predict what an unknown application is, whether that prediction is going to be normal or botnet will depend on the features that are extracted from that application. So what is unique here about the work that we've done is the fact that we are applying feature vectors directly to the CNN-based classifier in the form that they are without any further pre-processing and without converting this into images. So a lot of the work that has been done where convolutional neural networks or other type of deep learning have been applied entails converting the vectorized application representations into other forms, especially images. And this is because of the fact that convolutional neural networks are more well known to be used in the domain of image classification and video classification and that kind of thing. So in this work, we aim to use our raw feature vectors without actually converting them first and see what kind of performance we're going to be able to get out of this. The obvious advantage of that is the fact that our computational complexity is going to be significantly reduced. So talking more about the feature extraction, we are actually applying 342 features which come from 5 different categories. We extract this from the applications or the APKs as they are known using a tool that we developed in Python. So we extract API calls from the executable. We also extract permissions and intents from the manifest file. We look for command signatures and characteristics of apps like the presence of other embedded files. Now, these features, like I mentioned before, are processed into a binary representation that will characterize each of the applications that are present in the training set. So let me talk a little bit about convolutional neural networks. As we all know, it is an artificial neural network type that belongs to a family of deep learning techniques. It works well for identifying simple patterns in the data, which can then be used for more abstract feature extraction in the deeper layers. So normally you will have two different types of layers in a convolutional neural network. You have a convolutional layer and a pooling layer. The convolutional layer extracts the optimal features. So we can look at the convolutional layer as a feature extraction layer, whereas the pooling layer reduces the dimensions of the convolutional layer features. So this can be likened to a dimensionality reduction functionality, or feature selection and reduction, which is normally used separately, or which is normally performed separately when other machine learning techniques are used. So with the use of CNN, we eliminate the need for feature selection, feature ranking and feature selection. Now, because our features have one dimension vector representation, we will apply the one-dimensional convolutional neural network, which is shown here in this figure. So basically, this is the architecture of our model. So we have created a model that has two convolutional layers and two max pooling layers, and a fully connected layer that does the final classification. So as you can see at the extreme left of the figure, we have our input layer, which has a dimension that is equal to the number of features. That is 342. And then we have our colored filters here that represent our feature extraction or our feature detectors, as they are called. So as the feature detectors slide across the vectorized input data or the input representation, we then get our feature maps. And these feature maps are going to be, the dimension of these feature maps will depend on the number of filters that we have. So the higher the number of features we have, the higher the number of feature maps that we have. So therefore, the more complex our model becomes. So we then apply a max pooling layer to reduce the dimensions of these feature maps. Then applying another convolutional layer, we have the same operation, which involves sliding our filters across the resulting max pooling layer to get a second set of feature maps that are then reduced by using max pooling. So finally, we flatten this out, and then we apply it to a dense layer, which contains 8 units. And at the end of it all, we have a single layer, the output layer that consists of a single unit that will classify our application, our app, into botnet or normal. So in a nutshell, this is the architecture that we have used for our botnet classification problem. So in terms of the data set that was used for this study, we've used a publicly available botnet dataset known as the ISCX dataset, and it contains 1,929 botnet apps belonging to 14 different families. And these have been used in some previous works, which I'm going to present at the end, because we're trying to see what the kind of results that we got look like in comparison to previous works. So this has been used by other researchers, and they applied various types of machine learning classifiers to it, including convolutional neural network as well. So we have 4,873 clean applications that are used in conjunction with these botnet applications for the training. So in total, our work is based on 6,802 applications. So this data set is publicly available. It's known as the SCX dataset. Now, I'm going to present the results of the experiments that we've done. The performance metrics that we use are accuracy. So this is the overall prediction accuracy, precision, recall, and the F1 score. So our precision gives us an indication of how good the model is at identifying a particular class. So if we have false positives, the more false positives we have, the less the precision we're going to have. Our recall is simply the posted prediction rate. So the recall value that we get indicates how good our model is at identifying the particular class. So in this case, we are considering the Botnet to be the reference class. F1 score is a weighted measure of weighted average of precision and recall. So the experiments we did were, first of all, the preliminary ones, which were designed to help us get the optimal configuration parameters. So the first one was the impact of the number of filters. So we vary the number of filters, increase the number of filters, and try and see where we are going to get the best performance. The length of the filters as well. We vary the length of the filters in order to get the optimal length, and the effect of the max pooling parameter. Now, the max pooling parameter is a parameter that gives us a ratio that determines how much dimensionality reduction we're going to do. The main experiments were comparing our CNN model with other machine learning classifiers. And then also, this went experiments where we put our results side by side with other works just to see how good the approach that we are investigating performs. Now, before I go on to talk about those results, these two graphs that are presented here are showing the training cycles or the training epochs. This is a typical training graph that you get when building the models or trying to fit the models to the data. So what you can see here, we have training loss and validation loss on the left. So the training loss is, we are tracking the loss that occurs from the models that have been built when we test this model on the training set. And the validation loss is the same metric being tracked when we test the model on our validation set. So the fact that you can see that these two are quite close together is an indication of the fact that we are not in the territory where we're overfitting our model. Also, this also shows us the effect of this stopping criteria that we have applied. And that criteria is whenever we have 100 epochs or 100 cycles of non-improvement, we stop training our model and we take the one that has the least loss or least validation loss as the best fit. Now, let me go on to the preliminary results. So as you can see on this slide here, we have the first one, which is the effect of the number of filters. And when we increase the number of filters in both layers from 4, 8, 16 to 32 and 64, we get an improvement in performance. By the time we get to 32, that's where we get our optimal performance. And what you will notice is that the more we increase the number of filters, the more parameters that have to be trained. So therefore, our model is becoming more and more complex. We are spending more time and more resources in trying to train the model. The other one I mentioned before was effect of the length of the filters. As you can see here, when we increase the length of the filters, we barely get any improvement in performance. So the shorter length filters happen to give us the best performance. Now, the subsampling ratio, like I mentioned before, or the max pooling parameter shows us the extent of dimensionality reduction that we are applying. So when we apply dimensionality reduction of 2, we, of course, we have about 25,000 parameters. So as we increase this, we're getting less complex model, but the performance of our model is degrading. So as you can see, the optimal configuration for our model was 32 filters of length 4 using max pooling parameter of 2. And in the dense layer, we have 8 units. So When we compare our model with other machine learning based classifiers, we can see here with the F1 score, the convolutional neural network model performed the best in terms of Android botnet detection on this particular data set. So this was better than what we obtained with SVM, a plain normal artificial neural network, simple logistics, random forest, decision tree, rep tree, random tree, naive Bayes, and Bayes net. So the table here that's coming up next shows a more complete picture with all of the other metrics: overall accuracy, precision, recall, and F1 score. So the CNN can be considered to have performed better than the rest of the machine learning classifiers. Now, when we put our results side by side with other people's work, we find out that our overall accuracy was the highest that has been reported so far. Recall also the highest, and the precision is not the highest, but one of the highest. But the F1 score for the papers that have featured that particular metric, ours was better. Now, this paper here is based, all of these works, by the way, are based on the same ISCX dataset. Now, this paper here also applied convolutional neural network, but the difference between their work and ours was that they extracted permissions and then represented these permissions as images. So what they did was have a two-dimensional image for every application, which is the conventional way of applying convolutional neural networks. And they got a good performance as well of overall accuracy of 97.2%, even though we have different numbers of applications in our overall training and testing data set. So by the way, our approach will give much less computational complexity compared to that, because there's no need to, we will not be converting our own representation to images. So to conclude, we can say that convolutional neural network with one dimension feature vectors is effective as a machine learning based approach to detect Android botnets. No further pre-processing is required to achieve good results with the CNN models. Our binary feature vectors are sufficient, and the convolutional neural network based models can outperform conventional machine learning algorithms and the conventional artificial neural network models when it comes to detecting Android botnets using static features. So moving forward, we would like to incorporate an improvement to the training process by automating the search and selection of the key parameters to obtain optimal performance. So obviously, the way we were doing the selection of parameters was manual. So we would like to incorporate an automated process to search and select the optimal parameter automatically. Then we would also like to apply the CNN approach to dynamically obtain features or hybrid features where we have both static and dynamic features together. And also, if possible, we want to evaluate the long-term performance of the convolutional neural network models. So we want to see whether these models will be more resilient compared to other conventional machine learning algorithms when it comes to Android botnet detections over a long period of time. So that concludes my presentation. So if you have any questions, I'll be happy to answer them.
Thank you very much, Suleiman. We have plenty of questions from the attendees.
Okay.
I don't think that we'll have time to solve all of them, but I think that you can access them through the Q&A and you can type an answer later. So just to start, we have a question that says, what reverse engineering technique did you use to extract the features from the APKs?
Sorry, what?
What reverse engineering technique did you use to extract the features from the APK?
The reverse engineering technique, I showed it in, okay, I didn't show it in the slide. Basically is using a Python script that will convert the APK into, that will unzip the NPK and then convert the executable into what we call SMRiC. using backsmile. So that's the technique that I use. There are various tools that can be used. There's APK tool. So it depends on which one you want to use, but I use backsmile. That's what I use.
Okay, sounds great. Just to add a bit on that question from my side, how let's go for another question. It's going to be too long, mine. So there's another attendee that's asking how you keep the identities of the botnet apps to be trained when you represent them in binary format.
How I don't understand the question. How?
So I guess that he means that when you are converting the APKs to a vector of the features, how you know which features or which vector identifies or relates to each of the APKs.
Right. The features themselves, the way it is coded, you know what feature you're extracting. So it's a supervised learning technique. So you know exactly what feature you're looking for. So for each feature, you look for it. If you don't find it, then you have a 0. If you find it, you have a 1. So it's straightforward. And someone asked, what fold cross-validation did I use? 10-fold cross-validation was what I used.
Okay. There's another question that they are wondering, could you say what steps you took to prevent overfitting of the dataset?
Now, overfitting of the data set, there's so many techniques that can be used. One of the things I've considered a holistic approach. Now, the more complex your data set, your architecture is, the more chances of overfitting. So you see, we're using just 2 layers. We're not going beyond 2 layers. And there are other techniques that can be applied at the model level, like dropout, batch regularization. So those are things that relate to CNN, deep learning techniques themselves. And also one of the things I was doing was checking those validation and validation losses and training losses. And looking at the way they are. And sometimes I'll get a wide variation and I'll suspect that the reason for this was overfitting. And so this is something I understood from other researchers that when you track and monitor that type of graph, it might give you an indication of whether you might be in overfitting territory or not. It's very difficult to say, but there are general rules, some of these that I've mentioned now, that you can use to prevent overfitting.
Great. Is there any way for a malicious developer to hide the features that they want to use in the app, the APK?
To hide the features, yeah, it's possible to hide the features if they can get access to the way or the stage where you are actually extracting the features. They can obfuscate some things to prevent you from getting those features. So yeah, it's possible to do so.
Okay, I think we have time for one last question, which they are wondering why you stop at 100 epochs.
100 epochs, yeah, it's just resource. I mean, after 100, if you're not getting any reduction after 100, it's safe to say that you're not going to, your model is unlikely to improve. So that's why I just chose that number, because I don't want it to go on indefinitely. Of course, time and resources is a limitation. There's an interesting one here. If you I just want to address, which CNN model or network did you use for this study, and why did you choose that over models like BGG, GoogleNet, etc. Now, GoogleNet, BGG, and all of these are based at 2-dimensional models that are used for, they are pre-existing models that people use for image classification. So mine wasn't based on image classification, but maybe if I decide I want to turn my vectors into images, I might look at those. So this is just a hand design model that I created myself. I didn't use any existing one.
Great. Unfortunately, we don't have time for more questions, although there are plenty more. Thank you so much, Suleiman. It's been great.
Thank you.
And we are going to move to the next